12.3 volts at idle at 1000 revolutions per minute. That's the battery voltage. And yeah, that's clearly not enough. You need at least 13.8 volts for a 12-volt lead-acid battery to charge properly. At 12.3 volts, the battery is actually discharging. What if I rev it up? At 2000 revolutions per minute I get 13.7 volts. It's better, still not enough for a proper charge. And at 4000 revolutions per minute, same thing, 13.7 volts. Why am I taking these measurements? Simply because I went for a ride, rode for about half an hour, and then the bike wouldn't start again. The battery was too weak. I was able to restart by recharging it with an external charger. That means the battery is fine, and the charging system on the bike has a problem. So I'm taking the opportunity to make a video showing how a motorcycle charging system works. How to test the rotor, the stator, and the regulator rectifier. For clarity, I'll display diagrams of what I'm testing, and then we'll also see how to improve the charging system. This is on a Moto Guzzi Nevada, but many bikes use a similar system. Hi and welcome to Enjoy Wheels. To start, a bike's charging system consists of a rotor, which is a spinning magnet driven by the engine. On my bike, the rotor is behind this plastic cover. I'll remove it. Now we can see the rotor. The first thing to check is that it's properly magnetized. I bring a screwdriver close and yes, it's magnetic. Around the rotor is the stator, which doesn't move and consists of windings. On some bikes, the stator can also be located inside the rotor. Here, we can check that none of the windings are burnt. Looks good. Here's an example of a burnt stator. Now let's electrically test the stator. To do that, it needs to be unplugged. The connector we care about is behind this black plastic part, so there's a bit of disassembly to get to it. The connector is here. The stator wires come in here. They're the yellow ones on the black connector. I unplug it. Then I take my multimeter in ohmmeter mode. Since the resistance I'm measuring is very low, I subtract the resistance of the test leads. I touch the two probes together, let it stabilize. Then hit REL for relative mode. Then I put the probes on the stator wires and read the value. The service manual says we should see between 0.2 and 0.3 ohms, and that's exactly what I'm getting, 0.2, 0.3 ohms, so the stator's resistance is good. Next, we need to check for a short between the windings and the bike's frame. For that, I unplug one probe, stay in ohmmeter mode, no need for REL, and touch the frame or battery negative. It's showing OL4 overload, which means the resistance is very high, so there's no short. I move the probe to another stator pin. Same thing, OL. Good. Now, for the curious ones, we'll measure the stator's inductance. I take an RLC meter. I measure the inductance of the leads. 3.1 microhenries, that's the value to subtract. Now I connect to the stator. 0.421 millihenries. Subtracting the leads gives about 0.418 millihenries. Now we'll test the stator with the engine running. Stator still disconnected. I set my multimeter to AC voltage. I start the bike. Make sure you have a fully charged battery for this test because the battery alone powers the whole bike when the stator is disconnected. At idle, 1000 revolutions per minute, I read about 20 volts AC. The service manual says 20 volts AC. Perfect. At 4000 revolutions per minute I get between 64 and 67 volts AC. The manual says 65 volts AC at 4000 revolutions per minute, so we're good here too. We can now conclude that both the stator and rotor are good. After the stator comes the regulator rectifier. As the name suggests, it has two functions. First, the rectifier, represented by a diode bridge. The incoming AC signal is converted into positive-only cycles. Since the battery smooths the rectified signal, the output is DC voltage. The second function is regulation, keeping the voltage from exceeding a certain level, normally around 14.5 volts. 15 volts is the absolute max. This is a shunt-type regulator, meaning it diverts current to ground whenever the rectified voltage exceeds the regulation threshold. Yes, that's basically a controlled short circuit. Downsides, it gets hot and the efficiency is poor. Upside, it's simple, cheaper to build than a series or switching regulator, and very robust. Some bikes use a three-phase system. The principle is the same, but the stator has 3 windings and the diode bridge has 6 diodes. You can use a three-phase regulator rectifier on a bike with a single-phase stator, but not the other way around. So, how do we test this part off the bike? Let's remove it. Here it is. This is the original regulator rectifier. It's sealed. You can't open or repair it. The electronics are potted. Now let's test the rectifier part. The goal is to check the 4 diodes of the bridge. I put my multimeter in diode test mode. First, we're going to test the 2 diodes in the upper section of the diode bridge. I connect the multimeter's COM lead to one of the red wires of the regulator rectifier, that is, to the cathodes of the 2 diodes. Then I connect the V+ lead of the multimeter to the anode of one of the 2 diodes. We can read about 0.54 volts. That's the diode's forward voltage drop, so this diode is good. I connect the V+ lead to the anode of the other diode and read a similar value, about 0.55 volts. This diode is good as well. Now I'm going to test the 2 diodes in the lower section of the diode bridge. I connect the V+ lead of the multimeter to one of the 2 green wires of the regulator rectifier, that is, to the anodes of the 2 diodes. Then I connect the COM lead of the multimeter to the cathode of one of the 2 diodes, 0.54 volts. That's good. And the other diode reads 0.55 volts. That's good too. All 4 diodes in the diode bridge are good, so the rectifier section of the regulator rectifier is working properly. Now let's test the regulator section. We could spin a rotor and stator with a drill, but we'll do it differently. Here's the setup. We'll use a variable transformer to generate adjustable AC voltage. Be careful, this variable transformer is not isolated from the AC line. Use proper insulated gloves and follow standard electrical safety precautions. The variable transformer is connected to the AC line. To limit the output current and avoid exceeding the variable transformer's 1.6 amps limit, I add a 6 ohm 50 watt resistor in series. The resistor will dissipate R times I squared, that is, 6 times 1.6 times 1.6. At max output, it will dissipate about 15 watts, and yes, it gets hot. I connect it to the variable transformer output. Then I add an ammeter in series to set 1.6 amps AC. Then I connect it to one AC input of the regulator rectifier. This first test is with a brand new inexpensive regulator rectifier, the $30 one. Then I'll test the original one too. I complete the loop and power the variable transformer. Then we will set the output current to 1.6 amps AC, so I set the multimeter to AC current measurement mode. I adjust it to 1.6 amps AC. That's the maximum current the variable transformer can provide safely. Now I connect the regulator rectifier output to a battery, with a voltmeter measuring battery voltage. I unplug the AC line to safely connect the voltmeter and battery. I set the multimeter to DC volt. The battery is at 12.7 volts with the variable transformer off. I power the variable transformer again, set the current to 1.6 amps, and watch the voltage rise until it stabilizes. It stops at about 14.4 volts, so this regulator rectifier regulates properly. Now I repeat with the original regulator rectifier. Same 1.6 amps AC input, and the output stabilizes at about 14.5 volts, so the original regulator rectifier works. But that's strange. Earlier on the bike it would only reach 13.7 volts at 4,000 revolutions per minute. Why? Because the bike also has other electrical loads. Fuel injection, fuel pump, instrument cluster, lighting, and so on. In this case, the regulator itself isn't limiting the voltage. The rectifier section simply can't supply enough current under load. So how do we improve that? First, here's a table of the original readings. At 1000 revolutions per minute, 12.3 volts. I marked it red. It's below 12.8 volts, so the battery is discharging. At 2000 revolutions per minute, 13.7 volts. I marked it orange. It's between 12.8 and 13.8 volts. The battery isn't charging or discharging. Same at 4000 revolutions per minute. The first idea is to replace the regulator rectifier with a model that has a better rectifier section. Here's the new one from earlier, the budget Chinese unit that tested fine on the bench. I plug it in and mount it. We agree, it would be better to test it before mounting it on the bike. I reconnect my voltmeter to the battery and start the bike. At idle, 1000 revolutions per minute, 12.6 volts. A bit better than the original, but still not enough. Battery still discharging. At 2000 revolutions per minute, 13 volts, worse than before. At 4000 revolutions per minute, 13.5 volts, also worse. Conclusion: this regulator rectifier doesn't fix the problem. The battery never charges with it, and it even discharges at idle. I finally installed another brand new regulator rectifier, this time from Carmo. This is not sponsored. I paid $160, more expensive than the $30 one, but still cheaper than the $300 OEM part. No guarantee it performs better, though. It's a 3-phase unit with 3 yellow wires but works fine on single-phase systems. Let's test it. At idle, 12.4 volts. Not great. Battery still discharging. At 2000 revolutions per minute. Nice, over 13.8 volts. I get 14.05 volts. Battery is charging. I mark that in green. At 4000 revolutions per minute. 13.9 volts, also good. Battery charges too. So it's better. The battery charges as soon as you rev the engine a bit, but at idle, it still discharges. So what else can we do besides replacing the regulator rectifier? We can reduce the bike's electrical consumption, mainly by modifying the lighting. The idea is to replace filament bulbs that run continuously with LEDs that draw much less power. We're going to replace the 55-watt H4 halogen low beam bulb with an 18-watt LED bulb. It's a Philips Ultinon HL. Once again, I'm not sponsored at all. We'll also replace the front W5W parking light, which draws 5 watts, with a 1-watt LED. This one is an Osram W5W LED. And again, no sponsorship. Same thing for the rear position light, using a BAY15D bulb, which lets us reduce power consumption from 5 watts down to 1 watt. Finally, I'll also replace the license plate light. Just like the front position light, it's a W5W bulb as well, so we go from 5 watts to 1 watt there too. Overall, total electrical consumption drops from 70 watts to 21 watts, which is a savings of 49 watts. You might ask why I'm not replacing the turn signal bulbs. Because using LEDs can make the flasher relay think bulbs are burnt out and flash too quickly. Let's install everything and take measurements. Front position light. Good, it works. The H4 bulb for low and high beam. That works too. Rear tail light and brake light. Okay. and the license plate light. Everything at the rear is working. Now let's retest the charging voltage with the engine running. Voltmeter on the battery. Go! Idle test. Voltage climbs. We pass 12.8 volts, so the battery no longer discharges at idle. It climbs to 13.4 volts at idle. At 2000 revolutions per minute. 14.05 volts. Great! At 4000 revolutions per minute. 13.9 volts. Even though the 2000 and 4000 revolutions per minute results are unchanged compared to earlier, the big improvement is at idle. The battery no longer discharges. If you ride a lot in the city, that's a big deal. Before wrapping up, here's one last test to verify that the battery doesn't discharge when the bike is off. We'll put an ammeter in series with the battery to measure the leakage current. I disconnect the negative terminal. We connect to the ammeter. First, set it to the 10 amp range, and plug into COM. Set the multimeter to 10 amp DC mode. And connect the bike's negative cable to the red lead, and the black lead to the battery negative. The bike must be completely off. On the 10 amp range, I read about 1 milliamp. Switching to a lower range for more accuracy. 0.89 milliamps. That's very low, well below what would discharge the battery quickly. A 14 amp hour battery is 14,000 milliamp hours. At 0.89 milliamps, it would take 14,000 divided by 0.89, so about 15,730 hours. That's about 655 days, or roughly 1 year and 10 months to discharge completely. You're probably riding more often than that. One tip, disconnect the red ammeter lead afterwards so you don't blow the multimeter fuse if you switch back to voltage mode. In conclusion, I went from a bike whose battery slowly discharged every ride to a bike that now charges correctly. I had to replace the regulator rectifier with a more capable one and switch the lighting to lower consumption LEDs. Regarding regulator rectifier technology, you'll probably hear about MOSFET types. These use transistors instead of diodes for lower voltage drop and better efficiency. The two units I bought both use MOSFETs, yet the $30 one still performed worse than the OEM diode-based unit. A good diode design is better than a poor MOSFET design. As for accessories, I recommend avoiding add-ons that draw a lot of power, like heated grips, if your charging system is borderline. And if your battery isn't charging, don't forget to check wiring and fuses. Also note that not all LED bulbs are legal for road use, so check compliance before making changes. That's it for this video. I hope you enjoyed it. If you did, feel free to share, like, or leave a comment. Don't forget to subscribe to the channel, and see you next time on Enjoy Wheels.